in many other conferences, many speakers are simply interested in thermodynamic Wetteansatz, and I'm happy this exotic subject is living through this conference as well. Okay, so now, but the real talk is quantized heat flow through quantum Hole edges. Please, Mitali, go ahead.
First of all, I really wish to thank the organizer for inviting me and giving me the opportunity. And I really want to mention one more thing, that I think it's a lot of hard work of many of you, that people like me can still, make some contribution to this vast field. And I hope I can make more contribution in my new lab soon. So the work that I'm going to talk today about is almost 3 years old. Not almost, it's exactly 3 years old. And it's about this heat flow that we have already heard two speakers like Dima already talked about a lot of things. So I don't have to explain them to you. I will take it like you guys already understand. And also on Monday, David gave a brief introduction. So this work was done when I was in Weizmann and was working with Moti Heibloom, and these are my collaborators of this work. And I hope that none of us here present today have any confusion about that nu equals to 5½ is a non-abelian state. And thermal conductance we measured only because we believe that it can really add some new information. Though 5½ is not a simple structure to work with, but it's not, you will be happy to know that the Moti still keeps working, though I changed already 2 affiliations and I'm currently in Switzerland and hope to continue soon. But sorry, I didn't put his name, but his name is Vivash, who is continuing with Moti where I left. So if time will permit, at the end, I'm also going to share their couple of new results. Okay, so because all the theories have been done, I really want to be a pure experimentalist and want to walk you through what I did so far in order to gather the data that basically says that, yes, heat was quantized when it was measured in the 1D ballistic limit. Okay, so if we just go for a classical conductor, and we know that the sigma and the kappa, depending like, the electrical and the thermal conductance looks like this. But when we go to 1D ballistic transport, namely we are just considering one dimension, and for the rest of my talk, to be truthful, I'm strictly going to confine myself in one dimension. And so John Penry in 1983, it's long back, almost close to 40 years now, that basically said that thermal conductance for also 1D ballistic channels is going to be quantized. And the most beautiful point about this conductance quantization is that, as you can see here, there is no charge. And to add to it, like namely, it should not be different for bosons and fermions. But what basically made us interested in this question is that when we go to quantum limit of heat flow, like when we go for, this is universal for bosons and fermions, this was predicted, and I will show you people already measured before us. But then Gain and Fisher, after 15 years after Penry, almost suggested that they will also be same if it is abelian anion. Namely, for Laughlin quasi-particles, we should be able to measure the same quantization of heat as it's for bosons and fermions. But as I said, like what bring us to this picture was that there was certain hint that if we can really measure it correctly, maybe we can identify presence of Majorana mode in the system. And that's where our journey starts. And here I want to just tell you that, as I mentioned, we were not the first group to measure heat conductance for 1D ballistic channels. So the first work was done in Caltech, which was for phonons, and then there were followed by there was for photons works were done in Helsinki. And what basically gave us our inspiration is this particular work that was published in 2013 from a group of from Paris. And they actually showed for integer quantum Hall effect, indeed, like the bosons, even fermions are exactly following the quantization like Banerjee suggested. Okay, so we start here, and as I said that, for integer quantum Hall effect, it was already proved. So our question was, if Ken and Fisher are right, we really would like to test them for fractional quantum Hall effect. Namely, we understand that when the interactions are absent, they behave, the bosons or fermions all are similar. But if we switch on some interaction, which is simple for us in quantum Hall effect, you don't have to change the sample. What you do is like you just change the magnetic field, or namely the chemical potential, and you can go to different filling factors. So our motivation was to check for a few of these abelian state, and then to identify eventually that if 5-half can be identified as some non-abelian state. And of course, my entire talk doesn't have any surprises because the results have been already talked about. So what I'm going to invest some time in is explaining the experiment. So we are talking about thermal conductance. And that means that there has to be some hot reservoir, namely, some source of heat that basically is going to be flowing to something which is cold. So as we are, working in low temperature, getting a cold reservoir for us is not a problem because the fridge is cold. And let's say if we can really be smart enough to cool down our electrons, you can see that most of the time our fridge and our electron temperatures are similar, but not in the temperature regime that I will be talking about here. Is the story true? But at any rate, if somehow I can create a hot reservoir where I can, control the power that I'm putting into the system, and then measure the temperature that increases by this power that I'm putting, which I know a priori, then it's already in our hand that how much we are putting, how much power we are putting, and how much this temperature is rising by that. And then if we really go to a very low temperature, we know that this system will be in a way that now, of course, as I said, I'm going to talk about 1D channels. So the heat will be necessarily taken by these 1D channels. I'm talking here electronic channel. We can later on see what happens when we are replacing the bianionic channels. So namely, heat will flow from hot to cold, and we know the input power and the cold bath temperature. So we dissipate some power here to increase the temperature, as I said, and eventually we can say that, as we are in a solid state system, there will be definitely some electron phonon interaction, which we cannot avoid. So if we know how much power we are putting in the system, we can always say that there will be certain part of it which will be going through the electron or the ballistic channel, and there will be certain part that will be dissipated because of electron phonon interaction. Now, how do we do this in our experiment? So first of all, I really want to tell you that this experiment is really very simple as if there are difficulties because we are going to measure some small numbers, but the conception is very simple. All we do in this measurement or in this technique is to measure the temperature. Namely, we just want to measure the temperature of the electron of the ground contact, namely the cold temperature, and also the temperature of the heated reservoir. Because these are the two places which are interesting for us. The TM is the consequence of we putting power from outside, which of course we are controlling, and that is how we calibrate it. And T0 is important because this delta T will define how much heat is going to flow. And that exactly is what we are doing in this experiment, no more, no less. So as I said, this delta P is in our hand, we know how to tackle it. And so as you can see here, if we can simply find a way to remove beta from this equation, then the only parameter that we will be left with is kappa or K, that is the total conductivity. I just want to comment here that as you can see, if the temperature is very small, you can already get rid of this term that you don't bother about. But then if it's high temperature, where we know that, you know, these things are going to be comparable and going to be competitive, then we can also subtract for different number here. Sorry, this is for a single channel. If there should be a prefactor here for multiple channels. So if we change the number of channel that is taking the heat out, this part is not going to be changing, because this part is simply the electron phonon interaction that has nothing to do with how many channels are actually taking the heat out. Okay, so let me show you the actual device. I didn't take the same device like Dima showed, but the thing is that they are similar. So as you see in the center, this green small chunk, it's a metal, and this is our resolver, hot resolver. And this blue pieces that you see here, and similarly all of these, they are grounded, and this is our cold resolver. So how do we really heat these? So I think this is a blessing when we work with quantum Hall effect, and that we know that all the edges we know their resistances very accurately, and hence it becomes like the entire strength of this experiment also actually comes from the fact that in quantum Hall effect, there are certain things that we know with higher certainty. So I cannot tell you if I will be in a system where there will be some bulk will not be really, you know, insulating, I'm not sure if I can do it as accurately, because in that case, I will be losing some heat. So what happens here is this, that I am sending some current, and this current then gets into this contact, which contact is the only connection between this 1, 2, 3, 4 gray, a bit dark gray that you see. They are only similar copies of Hall bars. So these 1, 2, 3, 4 here, just you can take as many as you want. I will explain to you why it is important for us to have better statistics, that we wanted to take 4. You can go higher, not a problem, but it should not be less than 2. And so the thing is that we inject some current, and that current then gets distributed among the others, because, you know, everybody has some ground, and that goes towards ground. In this particular picture, what I wanted to show you is that we can actually put some gates which can manipulate how many edges that you want to go towards the ground, and how many you really want to kind of lock and not leave this small island. And as I said in the previous slide, that, you know, the electron phonon term is not going to change depending on how many green edges are taking the heat out. And what we are trying to do in this experiment is only try to manipulate these gates and control the number of green edges that is taking the heat out of this small island. Okay, so the entire experiment is simple. So what we do is, like, we inject some current, and we manipulate the number of edges that are going to go out of this small ohmic that I showed you in the center. And that way, what we do is, like, we can measure noise in one of the amplifiers. We can measure the noise, and that noise, by the way, if we can make sure that we do not have any extra source of noise that we are putting by hand. So namely, there are certain things that have to be make sure when we have a good device. If everything else is good, that means that the moment you have a device when you are not really generating some other noise, the temperature of this hot contact can be measured by simple Johnson-Nyquist in one of these drains. And that's all we do. So this is one simple trace of how it looks like when it's, when we change the number, when we scan more current into this small ohmic contact. And more current for us means more power, because the G star here is this R Hall of the particular state that I'm talking about. So this is a simple circuit that I represent exactly from the page before that you saw the device looks like. Okay, so what we can do here, we can change the number of red resistances by using the gate, and hence what we end up with is different such curves, which from the noise that we measured, we can simply go directly by using this formula. By using this formula, we can directly go from the noise to temperature, and that's what we are doing here. And then if we subtract these two certain, when I'm writing n equals to 2, n equals to 4, which all I mean that in this configuration, only 2 edges were allowed to take the heat out of the floating ohmic contact. And in this case, 4 edges were allowed to take the heat out of the ohmic contact. And as I mentioned before, that the phonon contribution only depends on the temperature, but not on the number of edge channels that is taking the heat out. We can actually take differences. And that difference will end up being, okay, so, and we take differences, and that difference will be getting rid of the phonon term, and we will end up only having this part. So this is what we are taking out of the question by taking the difference. And as you can see here, if we go to a lower temperature, it is almost straight line where we hardly have any T to the power 5 or the electron phonon interaction, that we have to consider here. But when we go to higher and higher temperature, of course, we have to, here we have to subtract the electron phonon. Anyhow, now let's go to the results. So as I said, the experiment is very simple in a way that this is all we do, and all we change in the sample is the chemical potential, and we go from one filling factor to another filling factor. And the only thing that we have to take care of this entire measurement, that, as I said, that we had to check that we are not introducing any noise in the system by hand, by doing something, or poor ohmic contacts, etc., because that is going to add to the noise on top of what we are supposed to measure, which will basically make our life difficult, and indeed it's a bad measurement. And the other thing will be that I showed you the device, and I said I have 4 similar hall bars that is connected with this reservoir in the center. Every measurement that I did, and I told you that I can subtract, I actually changed the number of, a number of edges. That means that I actually had to make sure that I had to make sure that all of these 4 arms are in the same quantum Hall state. Namely, there are these few things that are essential for this experiment to really fall in place. Anyhow, now if we do everything correct in the lab, and then if we and if we want to now start measuring for different filling factors, what we expect. So for electron, it was done, and it was shown that it was the fermions and bosons are similar. So now we first go to 1/3 Laughlin quasi-particle, and we wanted to see that what do we measure. And this is what we measure. This is basically delta n equals to 2, means I generally presented here you between 4 and 4 channels and 2 channels, and then this is the straight line, and you can see the slope is 1, and the factor that this prefactor comes with this kappa naught, like this K is the thermal conductance. So in the unit of kappa naught, all we measured is 1. And this kappa naught is the constant that I showed in my second slide. So basically, according to Ken and Fisher, it should not behave differently when we are in 1/3. Namely, interaction should not do anything to the quantization. And exactly this is what we got. And then what we wanted to really do is we want to go for some complex fraction before we jump on 5/2, because I can always tell you that in 5/2 I'm supposed to measure some fraction. Like I even showed that for Majorana we are supposed to see half. But I have to really prove to you that if there are other neutral modes which are not Majorana, they behave differently than what is expected of Majorana. And the good part about quantum Hall effect is that they are pretty handy. These neutral modes are pretty handy when we go to whole conjugate states. These are these 3/5, 3/5, 2/3, 4/7, etc. And thanks to Dima, he has already explained a lot of my data. So I will only show you the data and kind of move on. So what Ken and Fisher suggested that 2/3 should be 0, because I think it's nice, naively we can always understand, but all this number that I've tabulated here is for full equilibration in thermodynamic limit. Namely, the assumption is that we have a long length of samples so that both of these edges can actually equilibrate. And for 2/3, we are supposed to get 0, for 3/5 minus kappa naught, and minus 2 kappa naught for 4/7. And as you can see, the edge structure is supposed to be like this. Now, I will show you my data, which has no minus sign, just because it was a 2-probe measurement that is what I did. So in my data, when I actually measure, when it is minus, it comes up from the other edge. Namely, what they wanted to show, let's say if this is my lower edge of the Hall bar, then this minus kappa naught means the heat conductance is coming from the other edge. Namely, if you look at here and you see that left-hand side, if I have a hot reservoir and right-hand side I have a cold reservoir, then you can see that from hot to cold, only one edge is going, and cold to hot, 2 edges are coming. So in that way. Okay, so this is the data, and as Dima already said, and as I said, that there is no surprise in my talk at all. You can guess that for 4/7 and 3/5, we are very close to the equilibrated value. The quantization was very close, and I know you are looking at my error, but we are experimentalists. We have error while we measure, and sometimes it's also crucial. And the number that you see here, that is almost 1/3, which was intriguing for us because 2/3, 1/3 kind of rings, and we feel that okay, if it is already fraction, then there's no point of running towards 5/2. It's already kind of falling apart. But as I again said, that Dima explained that equilibration can give this kind of like not equilibration can give this kind of situation. For us at that time, what we did is just we increased the temperature T0, which is because we could not change the length of the sample. Instead, what we did is that we changed the temperature T0 and wanted to see if it is really equilibrium. Because if this 1/3 will be a God-given number, we are now so used to looking at quantum Hall, plateaus. We know that if it is really universal and quantized, it's not going to go down. You can always say, Mitali, things are not going down too much. Well, the temperature is also not changing too much. And if you think that why I didn't go beyond this number, well, I showed you already that as I go to higher and higher temperature, what happens that electron-phonon interaction kicks in. And then the error in my data will increase, and it will not stay here, but it will go like this. And then it will be meaningless to plot another data here. And that's the reason we stopped at the point that we thought that we see a trend. Anyhow, this is the portion that Dima already talked about. So I'm not sure how much the time I should be actually spending here, but all this model tells you that as we increase the number of edges, it's basically goes faster towards the equilibrated value, and hence for 4/7 it's faster than 3/5, and then it's for 2/3 literally we need the infinite length of the sample in order to go to the value 0. Okay, so now I want to really go towards 5/2, and like all of us are now know what is about this previous experiment. Like when I also started, I already knew, and few of the works were done in Moti's lab already. So I started from some background work that already was done. And of course, I was hoping for anti-Pfaffian wave function, and this is what didn't happen. But I want to just slowly just show you a small table, which was our motivation, that we wanted to land somewhere here, and that's how my mind worked. That if I measure this number, I thought I will be happy. But just there are various wave functions that can actually explain 5½ given the same sigma, like two people already talked about it. I don't want to spend time. I just want to show you the data that we have. And here for 18 millikelvin, you can see that I am very close to 2.5, while if I go into lower and lower temperature, of course, I have no control, and I only show you what I measured. But what we did is that we cannot lower more temperature, but we went to higher temperature, and we saw that the fact that it doesn't really go below 2.5. And it saturates almost at 2.5. And if you have a question like, Mitali, why didn't you go below 25 millikelvin? Well, the answer is, like, I didn't show you here the whole scan, but our RxX was quantized only until 30 millikelvin. As we go beyond that, it was RxX was not really 0. And if RxX is not 0 in our measurement, it affects us in a way, because we are relying that all the current that I'm sending in the system is only carried by the edges. So the moment I introduce some kind of backscattering in the system, I will not be able to capture all the current by the edges. Namely, there are grounds everywhere in the sample that I did, and current is going to go and flow towards any ground. And that way, my measurement will not be correct. And hence, we are measuring a small difference, and I would not be going towards something that will add error to my measurement. And we stopped here. Anyhow, this result is known for quite a while. What I want to add, and Moti and the first author of this paper is already here in the audience, so I thought it would be a good opportunity just to show that we didn't stop here, but Moti is continuing already. So this particular device is about having an interface between two different filling factors. And why this is important? Well, I think many of you can guess. Really do some breeding for higher Landau levels, we really have to go for a configuration where we can really work with one edge channel, which is fractional. Sticking towards the lowest Landau level, and that's something that is, not so flexible. Anyhow, let me go to the result for them. So why they needed, interfacing it, just because, when you go to interfaces, you can gap out few of the integer edge modes, and then you will be just left with something which is Majorana and the fractional charge mode. And here in this two, basically the picture is that if you consider anti-Pfaffian and if you consider pH Pfaffian, what do you expect in terms of when you measure, in a amplifier or in a contact? So the thing is that what they found in this paper is that their result actually, by just measuring simple upstream noise, actually supports this pH Pfaffian configuration, which for all of you can actually look at this reference. But what I would really suggest that I think it's a very fresh results, and I thank Moti for giving me this opportunity to share it here, and that they have actually measured thermal conductance now in this configuration, and the very preliminary data that they have shows that if it will be anti-Pfaffian, and we should be getting something like this, because there will be this, the half, the E over 4 charge will be moving in the half edge, like the edge for the fractional charge will be going alongside in a co-propagating manner with the Majorana, and that should give you 1.5. And when we have this pH Pfaffian picture, then they are actually opposite moving. And as we have already heard about equilibration a lot, I'm not going to go into this entire conversation, just to tell you that there will be two limits. If it is completely non-equilibrated, we'll give you 1.5, which will be completely matching with antipfaffian. While if will be completely equilibrated, then we are expecting something like this. While in this picture, they don't have to, so, they are gapping out only the integer edge modes here. And I would encourage any of you who will be interested in knowing about this experiment to attend this talk, which will be in EPQHS next week. And with this, I would like to thank you guys for your patience. And if there will be any question, I would be happy to take. Thank you so much.
Thank you, Mitali.